friends, in this video we will study the activation functions. So activation function is defined as generally activation function is used to calculate the output response of the neuron. So it is used to calculate the output response of neuron. So the question is why we are using the activation functions, because the output of neuron can be anything between minus infinite and infinite, because we don't know what will be the output of the neuron. So we have to map this output that is lie between minus infinite to infinite to some finite range, means some range, let us call this CD. So we map the this set consists of all numbers. This set consists of any number. So we will map this into finite number, so that when we take any number, then we'll map it to some definite range. This C or D may be equal to 0 1 or minus 1 1. That means any number, we will represent that number in the range of minus 1 to 1 and so on. So there are various activation functions. So let's discuss these activation functions one by one. So the first activation function is identity function. Identity function. So this function is given as f of x equal to x, means what is the input of whatever the input of the function, that will be the output for all values of x. That can be represented as, let us represent this by x, and this is fx, and 1 2 3 4 5 6, and again 1 2 3 4 5 6. So if this is 1, argument is 1, then the output will be 1. So this point, when 2, the output will be 2, when 3, the output will be 3, 4 again and so on. So, and when the input is 0, the output will be 0. So this function is like this. Let's discuss the second function. So the second function is binary step function. So this function is like this. Fx is equal to 1 if x is greater than or equal to some value theta, and 0 if x is less than theta. This theta, we can call this theta as threshold value, that is minimum value that will be required to output the function as 1. So we can represent this function diagrammatically as this. Same, this is x and this is fx. So let's, theta is here. So we see from this function that if x is less than theta, then the function value will be 0. So if we take this theta, any value less than theta, then the value will be 0, and suppose this is 1, any value which is greater than or equal to theta, that will be 1. It's like this. So any value less than theta is 0, and any value equal to or greater than theta, that is 1. This is 1. So the third function is piecewise linear function. this function is defined as fx equal to 1 if x is greater than or equal to 1 by 2, and x if x is less than 1 by 2 and greater than minus 1 by 2, and 0 if x is less than or equal to minus 1 by 2. So let's represent this diagrammatically. Let's take this point as 1 by 2. This is 1, this is anything 2, 3 and so on, and this is minus 1 by 2, and this is minus 1 and minus 2 and so on. So using this function we can see that when x, any value x is greater than or equal to 1 by 2, then the value of this function will be 1. Let the 1 is here. So when x is greater than or equal to minus 1 means here, then the value of function will be 1. And when the value of x is between minus 1 by 2 and 1 by 2, that is here, then the value of the function is that value itself. So this is represented like this, because between these values, when the input is something x between minus 1 by 2 and 1 by 2, then the output of this function is itself, and the output of this function is 0 if x is less than or equal to minus 1 by 2. That is, if x is less than or equal to minus by 2, less than or equal to minus by 2, then the value of this is 0. The next function is binary sigmoidal function. So this function is given as fx is equal to 1 by 1 plus e to the power minus sigma x, where sigma is known as stiffness parameter. Now we will find the range of this function, for which we differentiate this function. So after differentiating this function, that is f dash x this f dash x will be equal to sigma fx 1 minus fx equal to 0, and we know that sigma can't be 0, so either fx equal to 0 or fx is equal to 1. So from this we see that the range of this function is 0 and 1. So if we represent this function graphically, that is, this is x and this is fx, then this function lie between 0 and 1, and these are s-shaped curves. So this function is lie between, this is 0 and this is, suppose this is 1. And if we increase the value of this sigma, then the curve will be like this. Okay. Now the next function is bipolar sigmoidal function. So this function is given as g of x is equal to 2 of fx minus 1, whereas this fx is binary sigmoidal function. We will also find the range of this function by differentiating this function. When we differentiate this function, we will get 1 minus gx 1 plus gx, and we equate it to 0 to find the range of this function. Then we can see that here sigma can't be equal to 0, hence either gx equal to 1 or gx is equal to minus. So gx is equal to 1 or gx equal to minus 1. So we can see that the range of this function is lie between minus 1 and 1. So if we represent this function, this is x, this is gx. So this function is lie between minus 1 and 1. Let us take this is minus 1 and this is plus 1. So this function is lie between here. Okay. Now the next function is hyperbolic tangent function. Which is f of x equal to hyperbolic tan of x. We can also write this as 2 upon 1 plus e to the power minus 2 x minus 1, and we can represent this function almost same like binary sigmoidal function. This function also lie between the minus 1 and 1. The next function is ReLU, that is rectifier linear unit. This function is defined as f of x is equal to max of 0 of x, means x of positive, means when the value of x is negative, then the output will be 0. It is when x is equal to negative, then f of x is equal to 0, and when the value of x is positive, then the value of fx will be x itself. So we can represent this as, this is x, this is fx. So we can see that when the value of x is positive, then it is x itself. So when the value of x is positive, then it is x itself, and when the value of x is negative, then it is 0. Okay. Next function is a variation of ReLU, that is leaky ReLU. This function is slightly different from ReLU. So here fx is equal to x if x is greater than 0 and fx is equal to 0.01x otherwise. So we can represent this graphically as, this is x, this is fx. You can see that when the value of x is greater than 0, that is positive, then the value of function is x itself. So this is like this. And when otherwise means when the value of x is negative or 0, then it is 0.01 into x, means this is slightly here. When negative, it will be multiplied to 0.01x, then the line will be like this. So the next function is Gaussian function. This function is used in RBF network. So here fx is equal to e to the power minus x square, and we can represent this graphically as here. This function is live between this minus infinite and infinite. Thank you.